Okay, so we can also, basically, because 2 factorial is just called, just 2 times 1, 2 times 1 less than itself. We can do the same thing over here, 7 times 6 times 5 times 4 times 3 factorial. So now we're saying 3 times 2 times 1, and so forth with the 7 times 6 times 5 times 4 factorial. And those are all different ways of expanding 7 factorial. Now we'll see why that is useful for us later on. Here is the definition. By definition, n factorial, by the definition that we're using, is whatever the number n is, times 1 less than the number, times 2 less than the number, and so on, until eventually we hit 3 times 2 times 1. This causes some limitations that we have to talk about. It has to be a whole number. For our definition, 6.5 factorial and negative 7 factorial don't work. Negative 7 times negative 8 times negative 9, we're going to hit positive 1. So we can only use whole numbers. For reasons I will show you later on, we are going to define 0 factorial as 1. And the way I see it, and I'm not exactly sure if this is mathematically correct, since we're going to be using factorial notations in rationally or equations or fractions, we can't really say 0 factorial on the bottom of a fraction can't be 0 because, well, we have a non-permissible value on the bottom of the fraction. So any number can be written like this. Any variable can be written like that. So 4 factorial can be written as 4 times 3 factorial, 4 times 3 times 2 factorial, or 4 times 3 times 2 times 1. All of these are going to be 24.
And it's really? Then there's a problem with the notes. For P6.
There's no page for that, right? I thought I caught all of them. All right, well, we'll stop that. We'll I'll be back right away because I made a mistake.
You got both sides. Was just one person using both sides, or was it just one person that got both sides?
So, back to where we were, because I was making two errors. So, find page 2, please. Now, what this allows us to do, the different ways of writing the factorials allow us to basically take your calculator out of this. If I want to write, if I want to know the number for 10 factorial over 7 factorial, yes, obviously we are able to do that with a calculator. But 10 factorial is going to be a bigger number. How many times bigger? I don't know. But I'm going to write this as 10 times 9 times 8, and I'm going to stop at 7 factorial. Why do I stop at 7 factorial? Because now I have a number divided by itself. I don't know what 7 factorial is. I do know what number 7 factorial is, but you don't need to. And then you should be able to multiply 9 by 8 to give you 72 by 10. This works out to be 720. Now, yeah, okay, calculator. But eventually, your calculator is going to go, no, I can't do that number. Factorial gets big very, very quickly. The values for 1 through 10, or 1 through 8 factorial, say 1 through 7 I know. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. 4 factorial is 24, 5 factorial is 120. 6 factorial is 720. 7 factorial is 5,040. 8 factorial is 50,000 and change. I don't remember what it is. It gets big very, very quickly. Actually, it gets bigger than anything else. Even exponential. It takes 2 to the power of 10 is only 1,024. So for 8 factorial, once again, I'm going to look what's the bigger number. The numerator in this case is the bigger number. 8 times 7. 8 times 7 times 6 times 5 factorial. I'm going to stop right there. And then in my head, I'm going to do 3 times 2 times 1. 3 factorial is 6. So our bottom can be written as 6 times 5 factorial. Once again, we have 5 factorials crossing off. We have the 6's crossing off. The answer here is 56. Now this is where my calculator, when I was in high school, told me, no, not going to happen. This comes up in a lot of problems. My calculator could not do 52 factorial. So I had to learn this. 52 times 51 times 50 factorial over my 50 factorial. Again, whatever they are going to divide to 1. 2, 6, and I don't remember, 2625 or 2650? I can't remember. 2652. 52. Okay. Your calculator, well, the black 84s top out at about 69 factorial. I have no clue what that monster is going to top out at, and I don't really care. I don't even want to show you what the factorial button is. We can also do this with just variables. We tend to use n for variables instead of x, because this tells me that, or when I see n, we tend to think, okay, n is a whole number. So n factorial could be written as n times 1 less than itself factorial. N plus 2. Well, it's going to be the number n plus 2. What's 1 less than n plus 2? N plus 1. What's 1 less than n plus 1? N. And that's why, and here we stop with n factorial. Now here, we have our definition. N minus 4 times 1 less than n minus 4 times 1 less than n, or 2 less than n minus 4, and so on and so forth until we eventually hit 3, 2, and 1. So I would take this entire statement here and write it as n minus 4 factorial. Make sure you have the brackets around it, because this is a completely different thing. N minus 24 is what that one works out. Do I expect you to memorize the factorials? Well, it's not necessary. It's definitely useful to have up to probably 5 factorial memorized. As you notice, I only had up to 7 factorial memorized myself. I know approximately it's going to be 50,000 for 8 factorial, but after that, I just don't. It's not necessary. We can take variables and reduce this. And this is where that idea, what is bigger? Well, in this one, the numerator is bigger than the denominator. N plus 2 factorial, so what's in the brackets is bigger than the n down here. So I'm going to expand the top guy. N plus 2 times 1 less, and n plus 2 times 1 less than n plus 1, or 2 less than n plus 2. And at this point, I recognize I have the n factorial on the bottom. What's bigger? A number minus 2 or a number minus 1? Number minus 1. So in this case, I'm going to manipulate or work with the numerator, or sorry, the denominator. So I'm just going to write the n minus 2 up top. Keep the exclamation point there, the factorial notation. N minus 1 times 1 less than n minus 1. Hey, I can stop expanding at that point because now I can see those are going to divide to 1. Now, here we often make a mistake. What's the actual, or what's the answer here? The numerator is 1, the denominator is n minus 1. We sometimes forget that we still have a numerator in that case. Now, in this case, we have, what's bigger, n factorial or n? Anything, except with the exception of 1 factorial and 2 factorial, the factorials are always bigger. So if I want to simplify this down, I'm going to expand the top. And at this point, I'm going to say, okay, I can, oops, I went too far. I can say, okay, I got an n minus 1 on the bottom. I guess I didn't go too far. So, that wasn't what I wanted. And if I stop here, I can cross my n's off. I can't cross this off, because this is n minus 1 factorial over n minus 1. I have to go a bit further. I have to go to n minus 2 factorial. Now, the n simplify to 1, the n minus 1 will simplify. We're left with an equivalent expression of n minus 2 factorial. This guy's the same way. What's bigger? 2 times n minus 3 or 2 times n minus 1? 2 times n minus 1. Now, obviously, I forgot to put factorial in there, if you could do that for me, because they were just, otherwise they were just nothing. So, I'm going to take the larger one. I'm going to leave the 2n minus 3 factorial alone. 2n minus 1. 2n minus 1 less, 1 less than 2n minus 1. And then 1 less than 2n minus 2. I keep taking 1 off. Again, I notice that those guys will cancel off. We're left with 1 over 2n minus 1, 2n minus 2, which we could expand if part of the question is asking for. We are, in this case, we're asked to solve this guy that has this factorial. And if I just give you n minus, if someone gives me n minus 17 is equal to some number, so n minus 17 factorial is equal to some number, I go to trial and error. I don't have the ability to solve that question. This question I do. Because we have irrational with this equal to some number. But we got to get rid of factorial somehow. We don't know how to work with factorial, so we got to get rid of them. The n is the larger number. So I'm going to expand the top just like we did before. I'm going to keep that 42 there. By expanding the top, now I can get rid of that annoying factorial notation. From here, now I have a second degree function. The only way to solve a second degree function is to get everything on one side, and I've done some quick expansion here. Get everything to one side and make it equal to 0. Two numbers that multiply to negative 42 and add to negative 1. Those two numbers are -7 and +6. This factors out to n minus 7, n minus 6. The solutions are n is equal to 7, n is equal to -6. Now, here's the thing. These are the solution to this equation here. If I plug them in, they're going to solve this equation. But if I plug them into here, check, make sure that they solve that equation. So if I go 7 factorial over 5 factorial, yeah, that's equal to 42. 7 times 6 times 5 factorial, that crosses off. What's wrong with this? What's wrong? Yes, Sean? Okay. Remember our definitions that we have are, if we're doing any type of factorial, we have to have a whole number, a positive integer. So this one here is not a solution because -6 factorial is not defined in what we're doing. Okay. Now, I have arranged for you all the letters in the word rose. There are 24 distinct arrangements of the word rose. Don't want to do anything more than that. It's a 5-letter word, now we're at 120 and I'm done. What happens if I replace the E with another S? So I'm going to go through and cross off all the duplicates on this one and see how many letters, how many distinct, how many completely separate arrangements there are. Okay, we got Ross, he's a double. We got RSOS and an RSOS there. We have RSSO, we have another RSSO there. We have an ORSS twice. We have an OSRS and an OSRS there. We have an OSSR and there. And then we have, where is that guy? SROS is there. And they're basically the same thing. So I'm crossing off those that are doubling up. SRSO is there. That one is over there. That one is there. When you count that, if you notice I was crossing off 1 for everything, there are 12. There are basically 12 distinct, completely different arrangements of the word Ross. So we can't use 4 times 3 times 2 times 1 like we could for Rose. That would give us 24. And if I replace the O with an S, to get us this incomprehensible thing, RSSS, watch what happens. That guy, that guy, that guy, that guy, that guy, all disappear. They're all RSSS. So even flipping those guys around, they disappear. This one here, we have SRSS. We have another SRSS there and there. We have one there, and we have one there. There were 6 of them. SSRS, that guy shows up there, and there, and there. Missing one, aren't I? SSRS. I was missing one there. And finally, we have SSSR. There's there. Oh, I stripped off that guy off earlier. What we end up with is we have 4 distinct arrangements. So there are 24 in rows and 4 in RSSS. Now, going back for a minute. How do I go from, what do I have to do to 24 to get to 12? (24) divided by 2 is 12. Now, if I think about this in factorial notation, 24 is my 4 factorial. 2 is written in 2 factorial. Here we have 24. What do we have to do to get to 4 if we start with 24? Well, we need to divide your 24 by 6. 24 is 4 factorial. 6 is 3 factorial. Okay. Basically, what we're looking at here is, in both cases, we had 4 factorial over 2 factorial when we had 2 repeats, 4 factorial over 3 factorial when we had 3 S's. This leads us to the ways that we can do this. If you have repetitions, okay, if there were no repetitions of the word in the word RSSS, there would be 24 ways to do it. 4 factorial, 4 times 3 times 2 times 1. There were repetitions. So we had to divide by the number of repetitions factorial to do that. And so our expression here is going to be, if there are n objects in something, we would arrange it n times n minus 1, so n factorial. If there are 2 a's, we would arrange it a factorial times b factorial times c factorial, and so forth. God, go away. I'm just going to show this. It's about 4 minutes long.
here's a question. My name is Jim. How many ways can we rearrange the letters of my name? Well, the answer is by the brute force method, just literally rearrange the letters and count how many ways. For example, it could be Jim, it could be Jimmy, it could be Image, it could be Ijim, or it could be N-Iji, or it could be Image. So 6 ways. But let me think of this as a multiplication problem in terms of doing several tasks. We take about 3 tasks. Those are 3 slots to fill. And our first task is fill in the first slot. My second task is fill in the last slot. First task, fill in the first slot. Fill in the second slot is my second task. Fill in the third slot, my third task. Alright, how many ways to complete each task? Well, there are 3 ways to complete the first task. How many ways can I fill in the first slot? All 3 choice letters, 3 ways to complete that. How many ways can I fill in the second slot? Well, I've already used that 1 letter, that means I need 2 letters to play with, 2 ways to complete my second task. And how many ways can I complete my third task? Well, I've already used up 2 letters, there'll be 1 letter left over, so only 1 way to complete my third task. And the multiplication principle says how many ways to complete all 3 tasks together? Well, the answer is 3 times 2, which is 6 ways, times 1 is 6 ways. Bingo, 3 over 6 ways. So actually, my name is James, that's my formal name. So I'm using that more lately. So how many ways can we rearrange the letters of James? Well, to me, that's really a 5-task problem. I have 5 slots to fill. There are 5 ways to fill in the last slot, 1 of 5 letters. There are 4 ways to fill in this slot, because I only use 1 up. 4, 3, 2, 1. Then, who knows, I mean, order my tasks any way I like. We'll use the word order. But actually, those are ways to complete each of my 5 tasks. The multiplication principle says total number of ways to complete all 5 tasks will be the product of those numbers. 5 times 4 plus 3 times 2 plus 1, 220. In fact, we'll see, as you play this game, that products of the form 1 times 2 times 3 up to some number n arise a lot, and people call that n factorial. That's the shorthand. So 5 factorial is 5 times 4 times 3 times 2 times 1 would be 120. Oh, we're already going downwards that way as opposed to upwards. Because it doesn't matter. 3 factorial is 1 times 2 times 3, but we're going upwards rather than downwards, 6, and so on. So read the notes below this course, and below this video, excuse me, for some more factorials. They come up a lot, and they'll be our friends as we go through this particular work. Alright, but I've been putting the world around a little bit. My name is actually too nice. Jim James. What does my name say word Bob? I wrote all in capital letters, so there's actually 2 identical letters in this name. How many ways can we rearrange letters of the word Bob? Well, I could do by the brute force method, just literally write them out. I can see it's going to be B-O-B itself, or there's the verb, B-B-O, or there's a or something. Alright, 3 ways. Okay, that's grand, I can work my way through my brute force. But things get a little bit scarier if I do the word like cheese. Now, there is a way to think of this in terms of just completing tasks. It actually is not too difficult. That approach is written in this video. What I'm going to do now is actually take a different approach to this. I want to look at ways to rearrange the letters of the word cheese using the technique I've already done. Namely, it's a good problem solving strategy. Can I use what I've just done to help me solve the next little problem? Namely, if all the letters were different, this problem was easy to answer. And the trouble with the cheese is the letters aren't different, they've got some repeats. So here's a problem solving strategy. Can I imagine that these letters were different? What would the answer be? Alright, if the letters were different, maybe they're like E sub 1, E sub 2, E sub 3, then I know this is a 1, 2, 3, 4, 5, 6. This is a 6-task problem. 6 slots, 1, 2, 3, 4, 5, 6. So first task for the first slot, 6 ways. Second task for the second slot, or the 6th task, 6th one. I know the answer would be 6 times 5 plus 4 plus 3 plus 2 plus 1, 6 factorial. So the letters were different. The way to rearrange the cheese would be 6 factorial. But the E's aren't different. So what I'm going to do is be a little sneaky. I'm going to actually start listing all 720 ways of doing this. Let me clear the board. E1, H, okay, let me list all 720 ways to rearrange letters of the word cheese, assuming those E's are distinct. Here goes. One way could be E1, H, S, E2, E3, C. E1, H, S, E3, E2, C. E2, H, S, E1, E3, C. E2, H, S, E3, E1, C. You see I'm being more systematic. E3, H, S, E2, E1, C. E3, H, S, E1, E2, C. Alright, and then there's H, E1, E2, SC, E3, H, E1, E3, SC, E2, and there's something I1 as well. Alright, so I could list all 7 different ways, and I was a little systematic, so we can't get the basic structure of my answers the same. The real question is, there's 1, 2s, and 3s that distinguish the E's, that's something I created. They won't be part of the problem. So what happens if I get rid of those distinguishing features? Look at this group of 6. If I get rid of all the subscripts of the E's, you can see that all of these answers collapse into one basic answer. E, H, S, E, E, C. And all of this group of 6 will collapse to the answer H, E, E, S, C, E, and so on. So actually, everything collapses by a factor of 6. So my answer here is 6 factorial, which was distinguished E's, gets divided by 6. Now, I'll be very clear. What was that 6 really? You can see what I was doing here. I was going through all the ways to arrange the E1s, E2s, and E3s. This is only a little word problem, which I knew was 3 factorial. 3 times 2 times 1 equals 6 ways to do that. So I was really dividing by 3 factorial. Beautiful. So with the PEs, I did a basic answer so that they're distinct, and I divided by the fact how many ways those E's can actually collapse the answers that I got rid of the subscripts. Alright, let's go up a level of difficulty. That was grand. We're ready for it. Clean the board again. Okay, we're ready for the next notch up. This time let's rearrange the letters of the word cheeses. Alright, I got repeat E's and repeat S's this time. Problematic. So can I reduce this to a problem I saw before? Well, yes, if the letters are distinct, I know the answer. In fact, if this was E1, E2, E3, and S1 and S2, this is 1, 2, 3, 4, 5, 6, 7 letters. Put them into 7 slots. That's 7 tasks. The multiplication principle says the answer would be 7 times 6 times 5 times 4 times 6 times 2 times 1. 7 factorial 5,040. Alright, now, let me start listing all 5,040 ways of doing this. Brilliant. Wow. Let's see what happens. Get me one answer in the E1, C, H, E2, E3, S, or S1, S2, and E1, C, H, E2, E3, S2, S. Oops. Change the E's. E3, E2, S1, S2, E2, okay, it's going to be a group of 6 of all the ways to rearrange the E's within that. Another group of 6 of all the ways to rearrange the E's within that, and so on. So when I remove the subscripts to the E's, just as before, I know those groups of 6 will collapse. This answer will collapse to E, C, H, E, E, S1, S2. And then the next group will collapse to C, E, E, S1, H, E, S2, and so on. That means everything's collapsed by a factor of 6. And what's that 6 really? It's really the 3 factorial ways of rearranging those E's, so we divided by 3 factorial. Okay, I've still got the S's going on, S1, S2. But the thing is, at some point, I'll have this arrangement with the E's, C's, H, and S1 and S2. Later on, we'll have another arrangement of E, C, H, E, E, and the other S1 and S2 the other way. And those 2 answers, when I remove the S subscripts, will themselves collapse to just a single answer. Oh, my third technique is lousy. E, H, C, H, E, E, S, S. So when I remove the subscripts from the S's, those collapsed answers will collapse again by another factor of 2. In fact, that's really the 2 ways to arrange those 2 S's, S1 and S2, 3 divided by 2 factorial. So fraction divided by an integer is just 7 factorial, 3 factorial, 2 factorial. So these are down words a little scary, but there we go.
So, what I'll do after with that.
Okay, bad ball technique.
Okay, so just a fairly long explanation on how we got there. So that was that explanation. I think he does it better than I can. I don't feel like writing all that stuff down. So with Vancouver, we have 2 V's in the word. We have 9 letters. If those 2 V's were different, we would have 9 factorial ways to arrange that word. But the 2 V's are not different. Right? If I had put V1, V2, there would be 9 factorial ways. Obviously, they're not different. So, as he said, I can take this V and I'll swap them, but they still spell Vancouver, they're still distinct. So that's where that 2 factorial comes from. And I don't really care what that number is. It's a big number. The word mathematical. There are 12 letters in the word mathematical. If it was a 12-letter word with no repetition, there would be 12 factorial ways to do this. But there is repetition. I can rearrange those 2 M's into, I could swap them out. So those guys would still spell the word mathematical. I have to take that list out, 2 factorial. We have 1, 2, 3 A's. There are 6 ways to arrange, see we got mathematical, and there are 6 different ways to arrange those A's if they were A1, A2, A3. Well, since they're not A1, A2, A3, we have to divide by 3 factorial, which is that 6. And then the other one that we have that's a repeat is our 2 T's. And we would have to divide that 12 factorial by that to deal with the 2 extra T's. Again, I don't really care what that number is. It's a very big number. Somewhere over 1 billion, I think. No, maybe a couple 100,000. Okay, so that is your permutations with repetitions. We're going to do a lot of this. Monday's lesson has to do with that. If you have, like for my full name, if I wrote them all in capital letters, there would be 7 factorial ways over 2 factorial, 2 factorial, because I have 2 E's and I have 2 M's. We can apply this to this pathway. Okay? I want you to figure out how many ways to get from A to B, assuming you always must move in that direction or that direction. How many pathways can you find? Trace out how many paths you can find. It's a reasonable number. I know it's larger, but it's reasonable. If you do it systematically, it works better. Okay. That is interesting. Okay, that grew up real good. So, how many different ways can we do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10. Okay? However, each one of those pathways, I'm just going to pick one at random. Okay? This one here went right once, down twice, and then right twice more. Every one of those pathways has 2 moves down and 3 moves to the right. So just using this one, if I arrange those moves in the order, we have this word, RDDRR. Not a word, but it's an arrangement of things that are repeating. If they were all distinct arrangements, all distinct letters, A, B, C, D, E, F, there would be 5 factorial ways to arrange this. They are not all distinct. You have 3 R's that you have to account for. So instead of 120 arrangements, we're down to, where am I, 20 arrangements. And then I have my 2 D's. When we expand this, we are what we have there. We have 10 ways of doing this. 20 divided by 2. So, yeah. Pathway problems. This is one way to solve that pathway problem, assuming we always say we have to move closer to where we're going. Now, this is good for 3-dimensional pathway problems. It's good for nice simple ones like this, but if I start to take out middle pathways or middle, if I was to erase this guy here because there's a part there or something, then it won't work. We'll get into how we do that later. I don't know exactly what I gave you for homework. So attached, you have the I write 2 different pages, and so you have the I write pages there that you can work on.